Okay, so let's start the class. So I changed my mind. It's fine. You can take attendance now. I gave extra credit to those who show up last time. So it's okay. Because otherwise it's not fair. That will mean people have to wait at the end. So whatever. So test number 3, it's going to be a at-home assignment. So it's going to be 15% of your final grade, right? And I will open a window. Like you will have few hours, like maybe one day to do it, to accommodate everyone. And it's going to be open notes. I just need to give you a date. Like there is a date, but I want to make sure that we are not going to change the date. I will get back to you on that. So test number 3 will be about magnetism and source of magnetism. So that's what we are doing now. It's a lot of conceptual questions. So with the right hand rules. So it's very hard to get the answer from ChatGPT if it's conceptual with illustrations. So make sure you understand the concept. We have many right hand rules to remember. So that's why today the pop quiz, it's gonna be about those right hand rules. So I just want to go ahead and to go and review right hand rules, and then we will keep going. So lots of conceptual questions for test number 3. The math is easy from now on. What you have to worry about is not to space out during class and to understand the right hand rules. Okay, so the first rule we have seen, so it's a review. If you have current flowing, if my thumb here is a current flowing, okay, so if you have current flowing this way, so it could also be positive charges flowing this way. So with your palm here, you're going to show that the magnetic field is curling around. So typical pop quiz question, a magnetic field never ever diverge or converge. A magnetic field always curls around. So it goes from the north into the south if you have a magnet, but if you have a wire, again, that's going to be the current flowing or the positive charges flowing, and that will be the magnetic field curling around. Okay? If that will be the first right hand rule. If you have a negative charge flowing, you use your left hand, and that's going to be the magnetic field curling around. Okay? So that's rule number 1. Okay, so we talk about the magnetic field of the Earth, right? And this is happening because inside the outer core, everything happens like you have electricity flowing. It's not really electricity, it's just charged ions. So iron 2 and iron 3 and nickel. So it's charged particles flowing. So it's behaving like an electromagnet that will produce a magnetic field. Conceptual question. Remember, the geographic north is the magnetic south. The magnetic field goes out of the north into the south, back to the north. Okay? So easy conceptual question here. Another conceptual question, you cannot have a magnetic monopole. It's always a dipole. So if you have a north, you need to have a south. If you break a magnet in two, you still have a north and a south. You break it in two, a north and a south. You can have an electric monopole, so you can have a proton, you can have an electron, you can have a proton and electron making a dipole, but you cannot have a magnetic monopole. Okay, so I'm just reviewing. Then we talked about electromagnet. So, and here is rule number 2. Different, same right hand, different rule. Okay, so if you have a coil of current, right? So if you have loop of current. So if you have a current going into a loop here, so you use your palm. So this is the current flowing. The thumb here showing you the north pole. Okay, so if you have, it's called also a solenoid. Okay, so if you have loops of current flowing this way, that's going to be the north, and that's going to be the south. Okay, so a loop of current, doesn't matter if you have many loops or just one loop, it will behave like a bar magnet. This is the south and this is the north. Okay, and that's how electromagnet work. You can make your own electromagnet for extra credit. It has to work. It has to pick up some paper clips, for example, but the wire here has to be insulated. So it needs to have some varnish around. Okay, so you can make your own very easy. If you shove, so if you don't shove anything inside, the magnetic field will spread out into space. If you shove inside here an iron core, okay, what it will do, it will make the magnetic field stronger, right? So it will catch the magnetic field line and squeeze it inside. So you will have a strong electromagnet. So that's for right hand rule number 2. Okay, 2. Number 3, it's the magnetic force acting on a current carrying wire. So a wire with electricity flowing through inside the magnetic field. So we are talking about only the part of the wire inside the magnetic field. It will be acted upon by a magnetic force. That magnetic force can only deflect the current, right? So current is made of flowing positive charges. So each little positive charge flowing through will be acted upon by a magnetic force. That force is a deflecting force. Rule number 3. So we have 3. It's the third rule. Okay, you have to do it, you can do it different way. You can say, if this is the current flowing, or if it is the positive charge flowing, and the magnetic field is going this way because it's a vector, then the magnetic force will come out of your hand like this. Okay, the magnetic force will be perpendicular to the magnetic field and to the current. If the current and the magnetic field are parallel to each other, there is no force. If they are anti-parallel, there is no force. If they are 90 degrees apart, so right angle, like this, right, the force will be maximum. The magnitude of this force equals the current, okay, flowing through the wire times the length of the wire placed inside the magnetic field times the magnetic field times the sine of the angle between the magnetic field and the current. So if the angle is 0, sine of 0 is 0, so there is no magnetic force. That's the third right hand rule. Okay, there is a fourth one. I'm not going to bother you with it. That's a different way to do it. If you rather, you can do it with 3 fingers. If this is the current and this is the magnetic field, so these are vectors going this way, that will be the current, magnetic field going that way, that will be the magnetic force. Okay, so you see, for a magnetic force, okay, to act, first of all, you need a charge. Okay, so charge flowing, and that charge has to be flowing, so you need some motion, and you need to have some angle here between B and the current. No angle, no force. No charge, no charge, no force. And if the charge is not moving, no force. So if you have a neutron, it's no force. Even if the neutron is moving, no force. You need to have a charge. The charge has to be moving. It has to be moving, with a given direction with the magnetic field. Again, if they are parallel, anti-parallel, no force. And this force is a deflecting force. It deflects. It cannot accelerate. Okay, so again, this is a summary of everything. So for the pop quiz, you can use this slide. And then I went maybe fast at the end of last class. We talked about MRI, which is super interesting. But we talk about each time you have a loop of current. So you have current going through a loop. Okay, so you can use your right hand. It will behave like a small bar magnet. Okay, and we can define a new physical quantity that we call the magnetic dipole. Okay, so the magnetic dipole is just the current times this area here times the number of loops. Okay, so each time you have current going into a loop, okay, so looping around, then you can use your second, is that the second or the third? The second right hand, right? Going this way, it will behave like a bar magnet with the north and the south. And this quantity here is called the magnetic dipole. Okay, so by definition, it's just the current times the area. Okay, so this you don't have to worry too much about the math. What you need to worry about for the pop quiz of the test number 3 is that if you place, so that could be a bar magnet because it's behaving like a bar magnet, or it could be a small loop of current. If you place it in a magnetic field, it will rotate in such a way that it will align with the magnetic field. Okay, so imagine you have a piece of iron, this iron filing. Okay, no, here I had like some examples. So those little iron filing is like little pieces of iron. So they get magnetized, and they behave like small compasses, right? Small magnet. These are little magnets. And they will rotate until they align with the magnetic field lines. Okay, so there will be a torque. So they want to align themselves with the magnetic field. You see how it's rotating in such a way that will be the north here, that will be the south. It's like a vector. So it will rotate until it's aligning itself. In this case, it will reach the lower potential energy. Okay? So that's how an MRI works. So imagine you can visualize those little compass. It's like a small compass here. That's the north, that's the south. It wants to align itself with a magnetic field. So when you have an MRI, I don't know if I have a picture of an MRI somewhere. So when you have an MRI, those little nuclei, hydrogen nuclei, they are protons. Protons, you can think of them as spinning. So they spin. Because they spin, they will behave like small loop of current. They will behave like a tiny magnet. Okay? So if you have them inside the magnetic field, those little nuclei, they will rotate to align themselves with the magnetic field, so they will have a low potential energy. This is low potential energy. And then you can excite them with radio waves. Those nuclei will flip against the magnetic field. They get high, okay, because they get the energy, so they get high. And then when they relax, they go back, and they burp out that energy as radio waves. And radio waves comes out of your body, and you are highlighted with radio waves. Okay, so that's how an MRI works. So if you want to have more details, explanation, in Khan Academy has a special section for the MCAT, and they review MRI. So these little nuclei of hydrogen atoms, they have lost their electron. They behave like small magnet, right? Take your right hand. So this is the north and this is the south. If you apply a magnetic field, they will align with the magnetic field, so they have the lowest potential energy, and then you excite them with the radio waves. They absorb the radio waves. They get high. So it means they flip. Okay, so now they align against the magnetic field, and then when they come back, they relax, they go lower potential energy, they're gonna burp out radio waves from inside, from the tumor, God forbid, out, and you can see what's going on inside. Okay, so this is called tomography. So each time you have a little compass or magnet inside the magnetic field, it wants to rotate to align itself with the magnetic field. So typical pop quiz question. This one will have the lowest potential energy because it's aligned itself with the magnetic field. This one will have the highest potential energy. Okay, to get to here, you have to do work. You have to do. Okay, so you have to do it mechanically. So you have to take your magnet here and force it. Okay, so all the work you are doing goes into the potential energy. Or you can excite it with radio waves for the MRI. You let it go, boom, there will be a torque. It will twist about an axis of rotation. It will be acted upon by a magnetic force, and there will be a twist. Okay, there will be rotation. Okay, so I hope that so far so good. So where are we now? So that was for the MRI. So this is my side kick here. Then I go back to 3.1. So again, a loop of current. You can define a new physical quantity called the magnetic dipole, which is just the current in amps times the area, which is in meters square. Okay, and it wants to align with the magnetic field. Okay, so it's a big deal because it will explain how we can build motor, right? So if you have a loop of current inside the magnetic field, and that's what how a motor works, right? When I talk about motor. So anyway, if you have a loop of current inside the magnetic field, so for example, here I have a loop of current, and here in another life, in another universe, you see I built, so this is a very strong magnet. It has a north here, a south here, and here I have a loop of current. Okay, and when I'm going to connect it to the power supply, there will be a force acting on those sides, so there will be a torque applied. So it's going to start to rotate, and this is a motor. Okay, motor works because of the magnetic force. So you can turn electric energy into mechanical energy. So it's like how you make ATP. It's kind of the same way. You start with electric energy, you have high potential, and then those hydrogen atoms, they go down the potential, they make something spin. That mechanical energy combine phosphate, whatever, with whatever, and it gives you ATP. So it's kind of the same idea. It's a transfer of energy from electrical energy to mechanical energy. Okay, so you have a loop of current here. I can find the magnetic dipole if I multiply the current flowing through times the number of loops times the area. Okay, and it will rotate if there's a magnetic field. So let's say there is a magnetic field and the current is going this way. So can you see here? Magnetic field is coming from here to there. Let's say you have current flowing, it will rotate until it will align itself with the magnetic field. And then there is a trick where you lose contact and it will keep spinning. So that's, and my arms hurt. That's how a motor works. So let me give you the definition first. You can add that to your equation sheet because it's missing from your equation sheet. Okay, so if you have a loop of current, you take your right hand, another one, another rule, right? So you take your right hand here. So the current is flowing through here. Magnetic field is going. Okay, so what's going to happen? Look at your thumb. Thumb here is your magnetic dipole. So this vector wants to align itself to the magnetic field. So you have the loop this way. It's not happy with life. It has too much potential energy. So it's going to rotate until the thumb here align with the magnetic field. See, it's here. There will be a torque time until, again, this vector here align with the magnetic field. And then it will be happy and it will have the lowest potential energy. Okay, you can look at your book and see the computation, but the torque from physics 1 is how efficient a force is in applying a twist, right? So here you have a magnetic force. Use your 3 fingers or your hand. You have a magnetic force, so it will rotate. Okay, you can do it this way, or you can use this way. I think is easier, right? So you have the current flowing this way. Look at my thumb. It's pointing in this direction. So it wants to rotate until the thumb here align with the magnetic field. So the torque, the magnitude for the torque, it's going to be the number of loops times the current flowing through the loop times the magnetic field times the area times the sine, the angle between here and there. But you won't have to worry about it, right? So if I take my motor, and I will demonstrate a little bit later, but I multiply to have the torque applied to this loop. I multiply the number of loops. I know I have like 6 of them, times the current flowing, because I'm going to connect that to a power supply through the loop, times the area, which is width times length, that case about, okay, times the magnetic field from the magnet. Okay, so I hope this is clear, and that will be the definition. So let's take an example here. So which way it's gonna spin? First of all, you can look at the force here going this way, right? Do you see? Down and up. So obviously it's going to spin clockwise. That's right. Is it clockwise? Yes, it's clockwise. If you want to use your right hand, which I think is easier, take your right hand. The current is flowing this way. The current is flowing this way. Do you agree? So it wants to rotate such as the thumb align with the magnetic field. So it wants to rotate clockwise. It wants to rotate clockwise to be happy with the lowest potential energy possible. So you have 2 ways to do it, yes? Right? Okay, make sure that will be the hardest part of test number 3. And don't rely on ChatGPT because I'm going to put pictures shaded, right? It will be very hard. It will take you 4 hours if you use ChatGPT. But if you pay attention in class, you can do it in 15 minutes. Okay, so let's take an example here. So you have a loop of current inside the magnetic field. Again, like I have here, show you how it works. I can show you now so you get an idea. So I have a strong magnet. You see this is called north. In another life, back then, long time ago, once upon a time, okay, I don't know why it doesn't work. Okay, so you have the magnet. This is no. This is my loop. Okay, so you have area, number of loops. And this is my power supply. This is DC. It's about 5 volts. So I'm going to connect that here. Okay, and connect that here. And you have a motor. So there will be a torque. So the torque will determine how fast it's going to spin. So the torque will depend on the number of loops, the current, the area, and the magnetic field. You see that? Isn't that cool? Right? And I will show you how to, if you want to get extra credit, you can make your own motor very easily. I'm going to show you that. But let's get rid of the math first. Okay, let's do this one quickly. So again, it's going to be clockwise. Oh la 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 la. So the first question has nothing, I mean, it's just the magnetic force here. You see, the current here is going parallel to the magnetic field. So here there will be no force. Typical question, conceptual question, is there a force here? No, because the current is parallel to B, so there is no force. There will be a magnetic force here, and there will be a magnetic force there. What's the definition of the force? The magnitude of the magnetic force is the current times the length of the wire inside the magnetic field times the magnetic field times the angle, right, between the current and the magnetic field. But we don't have to worry about it because it's 90 degrees. Okay, so we're going to suppose that this is 6 centimeters, and we suppose that this is 8 centimeters. Okay, so you plug in it. Don't stare, do it. So it's going to be the current, which is 0.5 times 0.08 times 0.1 and sine 90. Okay, so we did that already last time. So I'm just finding this magnetic force, which is the same as that magnetic force. So this you can do in your head. If you are taking the MCAT typical question, 5 times 8 is 40, and then divide by 10, and then divide by 10, divide by 10, divide by 10. Okay? So doing it, right? So it should be 4 times 10 to the negative 3 Newton. Do you agree? Yes? So you have a couple here. You have a force pushing this way, a force pushing that way. It means it's going to move clockwise. Okay, so that's just a magnetic force. Because there is a force that makes it spin, therefore there is a torque. Okay, a torque is measuring how efficient is the force in making that rotation happen from physics 1. And the torque is by definition, not definition, you can compute, you can show that. It will be the number of loop times the current flowing through the loop times the area times B. Okay, so why don't you try to find this I'm not going to worry about the angle. in that case, the angle is 90 degrees. This here is a physical quantity called mu, which is called the magnetic dipole. So the magnetic dipole is in amps times area meter square. So anyway, just compute the torque. So the number of loop is 1. The current flowing is 0.5. Do it. The area is width times length. So 0.06 times 0.08 times the 0, and then the magnetic field is 0.1. So the notation for torque is tau, like T. Okay, so you do it. Are you doing it? There is nothing to stare at. I don't know what you are staring at. Just do it. So the answer will be 2.4 times 10 to the negative 4. Unit is Newton meters. Okay, so the unit for torque from physics 1 is Newton meters. Again, how efficient is the force in applying a torque? So once it's going to rotate like this, the magnetic dipole, which is your thumb, is aligning with the magnetic field. Again, it's going to be stuck. It's happy. Its lower potential energy is not going to move, and the torque will be 0. Okay? Now, another definition. I don't know if I have another definition. So you have, for in this class, you just have to worry, don't have to worry about the angle, but here, remember, if you take your right hand rule, that will be here, here. That's what we call the magnetic dipole. The magnitude is the number of loop times the current times the area. Okay, it's a vector, it's a physical quantity. And again, the loop will rotate until that vector align itself with the magnetic field. They want to be aligned with each other. So it will go from here. It's not happy with its life. It's going to rotate, right? And now it's going to be happy with its life. Yeah, life is good. Lower potential energy. The torque is the magnetic dipole times the magnetic field times the angle between the magnetic dipole and B, but that's more advanced. You don't have to worry about it, but that's the formal definition. At least understand the concept. If you have, again, a loop of current, you see the thumb, so that's like the north and that will be the south. It will rotate until it will align itself with the magnetic field. They have to be aligned. Okay? Lowest potential energy. If you want to make it against it, you will have to do work. Okay, so you learn that in chemistry, in advanced chemistry, you learn about spin. Okay, spin always, it will also associated with energy. Any question? So here it's the idea of a motor. So again, you have a magnetic field from north to south. again, again and again and again and again. You take your right hand, you have the loop, you see? Magnetic dipole will go this way. It's not happy. It wants to rotate to align itself with the magnetic field as shown here. At that point, you are losing contact. Okay, so that means it's not going to flow anymore. So it wants to get stuck, but it can't because it has inertia. So it will keep spinning and it will start again. That's how a motor works. Okay, this is the idea of a motor. So I have a simulation to show you here. So you have the magnetic field going from north to south. You have a power supply. The current is flowing through the loop. The loop will rotate such as the magnetic dipole will align itself with the magnetic field. It should be stuck, but it doesn't because it's losing contact, so it keeps spinning. So that's an electric motor. So the magnetic field is a way to transfer energy from electrical energy to mechanical energy. It's all about transfer of energy. Okay, so I show you the demo already. So let's see, I have a small video here.
Basically, a current loop that's placed in a magnetic field, typically between the poles of a permanent magnet or maybe an electromagnet, so we can do it either way. And that loop rotates. It's on some kind of bearings on a shaft. And here's the really clever thing. Toward the left there, you see a battery connected to this structure. But of course, the battery's stationary and this loop is rotating, so we somehow got to get the current in there. So we have these little semicircular rotating copper or other metal pieces, and we have things called brushes, which are typically made of wire or carbon, and they're contacting those rotating surfaces, and they're letting electricity flow through it. Here's the really clever thing. That connection is called the commutator, and you see a little gap there in the commutator. And what happens is, as the loop rotates, it would normally just align itself with the magnetic field, as we've just seen. But just as it gets near alignment, that commutator switches past that gap, and that reverses which part of the battery is connected to which part of the loop, and that reverses the direction of the current in the loop. And that means the loop is no longer in alignment with the field. In fact, it's out of alignment and it wants to rotate a whole 180 degrees to get back into alignment. And so it tries to do so, but just as it barely gets there, the commutator reverses the direction of the current again, and the loop just keeps rotating around, and that is an electric motor. And it's basically
Okay, so there is a lot of demo you can do. So that's just the same thing that I have found. So you have your battery, you have the current flowing, you have the magnetic field, and again, loop, you have your magnetic dipole wants to align itself with the magnetic field, but it's losing contact, so it keeps spinning. Okay, so it's the idea of a motor. You can build one. This one is a little bit challenging. You can find this video on YouTube. It's I did it, but it's challenging. I mean, you have to be good with your hand. Depends how good you are with your hand. And it's you need the enamel wire, meaning with insulation. And this one is totally you have to remove with a sandpaper. And this one you only remove 2/3. I mean, it's explained in the video, so that's worth a lot of points if you can get it for extra credit. But easiest one to build is called homopolar motor. So I don't know if I can show you. Oh,
so second. Well, what was that?
oh my God.
For emergency strikes, first responders rely on the latest technology. That's why T-Mobile
don't do Ozempic, right? Very unhealthy. So anyway, you see, it's very easy to make. You can find YouTube video how to make them. So you need a very strong magnet. They are called neodymium magnet. And you need a piece of copper. Doesn't have to be insulated or nothing. And you can make your own motor. It has to touch. So for that to work, the wire has to touch here. So what's going to happen? Electricity is flowing here, and then it's flowing through the wire, through the magnet, through the wire. So you have electricity flowing. You also have a magnetic field, so there will be a torque applied. If you are in art, this is very artistic. And you have good music too, okay? You have very original design. You can make your own design. Super cool. You know, you can be creative and you will get extra credit. Ah, the music is good. Have good music here. Okay? And of course, if you want to know the physics, let's see. Uh, I have a slide somewhere to show you how it works, okay? So this is the same demo, but with a screw here. So anyway, on top you have the power supply. So the current is flowing this way. You have magnetic field from the neodymium magnet, and you're going to have a magnetic force that will apply a torque. Okay, so even another one is with a screw. And it's going to start spinning. Even easier. If you want to make it easier, you have easier. Okay, so you can do that. Doesn't cost much. Everything is cheap with online. Okay, that's just a parenthesis. How to build a motor. Okay, so that comes from this one comes from your book. Okay, so how to build a DC motor. It needs to be applied a force. So back then, before we had multimeters to measure current or to measure voltage, they were using they were using the magnetic force. Okay, so for example, if you apply a current and let's say you want to measure the current flowing into your circuit that you just built, you have this device here with a loop of many loops. So have many turns, right? So the current is flowing, and again, it wants to rotate to align itself. So from north to south, the magnetic field is from north to south, from north to south, and then the current is flowing this way. Current is going into the screen, so it will rotate to align itself. Now, the amount it will rotate will depend on the current. Okay, you have a torsion like a spring here. So it will rotate, and the amount it rotates depends on the current. You can do the calibration, and you will be able to measure the current. That was back then. Okay, now we have electronics. So that was before electronics. It's called galvanometer, right? You can measure the current, you just have to calibrate. Okay, so let's try again to do this one, just to make sure you know how to apply the equation. Equation for torque, okay, is going to be the current times the number of loops times the area times the magnetic field add that to your equation sheet because it does not have that equation. Okay, so do that. More you do here, don't stop staring. Don't stare, do it. Okay, so the current is flowing this way. Again, the thumb is going to be your magnetic dipole. Just look at the thumb, that will be your magnet, north and south. So it's going to rotate, in that case, counterclockwise to align. So the thumb is aligned with the magnetic field. Why you have bulbs here. And so you do the computation. And don't stare. Do it. So again, in magnitude, okay, in magnitude, the torque applied to a loop of current will be the number of turns times the current flowing through the loops times the magnetic field times the area, and that will be the angle theta. Okay, and the angle is 90 degrees in that case. So it means we are doing this, right? So this is the current I. That will be your thumb. Okay, imagine this is your thumb. Okay, the magnetic field is this way. So in that case, the angle is 90 degrees. So it wants to rotate this way, which is counterclockwise, such as your thumb is aligned with the magnetic field. I don't know how to make a hand. This is your, I don't know how to make a, this is a hand. I don't know, it's not convincing, right? It's easier to show like this. It wants to rotate. And that will be the magnitude. So it's a torque. Unit is Newton meters. And this is the number of turns. Okay? So do it. So the torque will be number of turns in that case is 1. The current flowing through the loop is 5. Okay. The magnetic field is 30 times 10 to the negative 3. Okay. Times the area. So area doesn't have to be a rectangle, right? It could be just a circle. But in that case, it's a width times length. So it should be 0.1 times 0.2 times the sine of 90. Okay, so the torque, it's going to be 0, yes, 0.003, right? Thank you. Newton meters. Do you all agree? Oh, good. So it's going to be 3 times 10 to the negative 3 Newton meters. That will be the torque. Okay, a torque is how efficient the magnetic force is to apply a twist. It's a twist force. It's a twisting force, right? There will be a torque, so it's going to start spinning. Agree? So the unit for torque is Newton meters. Okay? Any question? So it's the thumb, right? So again, if you have loops of currents, the thumb showing you the north, this is the south. The thumb here is like a vector with a tail and a head. It wants to align itself with the magnetic field. See, magnetic field is here. This vector here wants to align itself with the magnetic field. That's the idea of an MRI. Okay, so let's try this one just to practice. It comes from your textbook, and again, it's missing from your equation sheet. So you can add that to your equation sheet, right? The magnetic dipole magnitude and the torque. And that will be the angle. But do it like I did before. So anyway, la 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 la. Magnetic dipole. Okay, so we're gonna find the equation that you can add your equation sheet. So magnetic dipole notation is mu. By definition, it's gonna be the number of turns times the current times the area. Okay, in magnitude, that will be the magnetic dipole. It's a vector. So if a loop of current is going this way, okay, you take your right hand, that will be your thumb. Okay, so that's going to be the magnetic dipole. So if you have, for example, a magnetic field going this way, right? So let's say you have a magnetic field going this way because you have a very strong magnet. So that wants to rotate this way, which is clockwise, to align itself with the magnetic field. So anyway, here they just want you to plug equations. So n is the number of loops, so that will be 100 times 0.045, and the area is given. So magnetic dipole is a vector, it's by definition. And I forgot, no, I didn't forget anything. Okay. Okay, do you plug in it? So 100 times 0.45, you can do it in your head, right? If you take the MCAT, you need to do it in your head. 45 times 2 is 90. And then you have times 100 divided by 1, 2, 3, divided by 1,000, divided by 10,000. So anyway, you should find 10 to the negative 4 amps. So this is amps, meter square. Okay? Yes? When they are not giving you any angle, that means it's 90 degrees by default. So mu is perpendicular to B when you are not given any angle. So this is A, B, find the torque. So the torque will be, you can say, the magnetic dipole times B times the angle between the magnetic dipole and B. We're going to say this is 90 degrees. So it's going to be the number of loops times the current times the area times B. And this is already the magnetic dipole times 1. Any question? Okay, so the torque, you just multiply magnetic dipole by B. So it's going to be 9 times 10 to negative 4 times the magnetic field, which is 0.15. Get that? Make sure I'm not doing any mistake. That's from your book. Okay, Cutnell and Johnson, and 1.4. Is that minus 4 Newton meters? Did you get that? Yes? Right? Don't stare and think I'm going to understand at home. If you don't understand here at home, you have other things to do in your life. So you have to understand here. You cannot let it go. That's the rule. It doesn't get better once you leave, because then you have other stimulation. Okay, magnetic moment, by definition, that will be the equation, number of loops times the current times the area. That will be the answer. Unit is amps meter square. The torque is the twist, how much twist, right? It's still going to be the magnetic dipole. Now you multiply by the magnetic field. That will be the angle between the magnetic dipole, so your thumb, the thumb, and the magnetic field. Okay, copy me. You good? 1062. Did you survive? Are we good? Right? And I have my sidekick here. Again, you see you have a loop of current. The thumb, that vector here is your thumb. It's called the magnetic dipole. Okay? It's not happy because it's not aligned to the magnetic field. So there will be a torque, a twist, a rotation, such as this vector will be aligned with the magnetic field. That will be the torque here. Okay, and it has some potential energy. Potential energy is minimum when they are aligned. It's maximum when they are not aligned. Same thing with the electric field. Remember when we placed like little seed inside an electric field, it got polarized. It's not happy with its life, and there will be a twist because it wants to align itself with the electric field. So it works exactly the same way. That's how a motor works, right? So again, let's do it the last time. But you seem to understand energy. And then comes the pop quiz, and then you are lost. But you understand. So plus is, where is the plus? Plus is in blue for some reason. It goes here and there, and then it comes back. So you see, it's gonna, so the current going this way, the thumb is kind of down. So it wants to rotate, such as the thumb is aligned with the magnetic field. The thumb is your magnetic dipole. Okay, so you will be good for the test number 3, right? I'm reviewing for test number 3. Mostly conceptual. I will open a window. Right, to do it at home, not in class. You don't need to have the GRC. You will have a big window to do it. You can do it in 20 minutes, and if you don't pay attention in class, it will take 4 hours. But you still do it. So anyway, motors are everywhere. We see those everywhere. They are cheating, right? Electric bike, hobbies, industrial, and in electric car. So motors are everywhere. Usually they are very demanding in current. Okay, so for example, mine, this one here. So you see this one is turning AC to DC. This is DC. And it's stepping down 120 volt to 5 volt. I don't need a lot of voltage, but I need a lot of current. You see, this wire is very thick because I'm going to drain a lot of current. A motor drains a lot of current. It's energy, right? So that's why if you have a washing machine, you have a motor inside. It's very demanding in current, very demanding in energy. That's why for the voltage, it's going to be 240 volt instead of 120 volt, right? To give enough current. Okay, so now we go to the magnetic force here, which is called the Lorentz force. But it's the same thing. So if you have magnetic force applied to a current is moving positive charges. So that means if you have a moving positive charge, right hand rule, inside the magnetic field, you will have a magnetic force applied to it. Okay, so the same thing, except now instead of having current flowing, you have a positive charge or negative charge. So if you have a negative charge moving, there will be a magnetic force applied and you use your left hand. If you have a positive charge moving, you use your right hand. Okay, and that will be the equation. So, for a charge to be acted upon by a magnetic force, it has to be moving, okay, and it has to be moving in a direction which is not parallel or anti-parallel to the magnetic field. That force is called a deflecting force. It will deflect, it will not accelerate. Okay, so let's see if I have some demo. So this is a very famous experiment. So you have a vacuum tube. So it's called the cathode ray tube. Remember, that's how we can produce X-ray. So you have an electrode here, cathode, which is negative. This is positive. That gets very, very hot. So electrons can get free. Okay. So this is negative charges. So electron, and they're going to rush to the positive electrode here. So you have a beam of electron. If now you bring a magnet close to it, you can deflect the beam of electron. Conclusion, typical conceptual question. A magnetic field can deflect positive or negative charge, but it cannot accelerate. It cannot change the speed. It can only curve or deflect. Okay? An electric field can accelerate, a magnetic field can only deflect. So let's say if I have a demo with the cathode ray tube somewhere on the rainbow of cathode. Yeah.
Straight Crookes tube, cathode ray tube, we need a high voltage power source, such as this one. We need the Crookes tube, which has a metal cathode, metal anode, a screen that has been coated with a phosphorescent material that gives off light when struck by electrons, and a bar magnet. As we turn on the screen, we notice that the electrons are emitted from the cathode, and as they strike the fluorescent screen, we're able to see the cathode ray, this stream of electrons illuminated. We can use a magnet to show the deflection of that stream. Here we can see the electrons being deflected by the magnet. The cathode ray moves upward. If we reverse the magnet, we would predict that the beam would be deflected in the opposite direction. And we observe that the beam is deflected downward. To demonstrate a Crookes tube, cathode ray tube, we need a high voltage power source, such as this one. We need the Crookes tube, which has metal cathode, metal anode, the screen coated with a phosphorescent material that gives.
Okay. So again, it's you can have, you see, you can have a magnet here. You have your beam of electron, and the magnet will deflect the beam of electron, right? So it's going to be very important because that's the idea behind a mass spectrometer. So first of all, I want to remind you from physics 1 before we go further. Do you remember about the centripetal force, right? So for example, if something is going along a curve, let's say you have a car here, right? So the car wants to go this way. If there is no force applied here, it will keep going along a straight line at a constant speed and it will go off curve. if you want the car to stay on the track, on the circular path, you need to apply a force, but that force is perpendicular to the velocity. Okay, the force here, okay, is perpendicular to the velocity. So what does it mean? It means it cannot change the speed. If you are pushing on the gas, the force will be this way. If you are releasing the gas, right? If you are brake, the force is going this way, so it can change the speed. If the force is perpendicular to the velocity, you are just changing the direction. It's called a centripetal force. That force comes from the friction in that case. It's the friction between the tires and the road that will provide that deflecting force, right? It will make the car stay on a circular path. The equation for a centripetal force is m, the mass, the speed square over the radius. So that's from physics 1. My point is that if you have a force perpendicular to the velocity, the force will deflect. It will not accelerate. And that's what's happening when you have a magnetic force. Okay, so if you have a magnetic force, right? So if you have a charged particle, let's say it's positive and it's going this way, and somewhere you have a magnetic field, and if the force is going this way, because there will be a magnetic force, okay, we're going to see that the magnetic force will be Q, the charge, times the velocity of the particle times the magnetic field. That force will make the particle deflected. Okay, it will make it go into a circle. Okay, the particle wants to go into a circle, it will be deflected, and that's called a centripetal force. Okay, so I just want to remind you of physics 1. If a force is perpendicular to the velocity, the force will not accelerate or decelerate the system. It will make it go into a circular path. It will change its direction. So let's look at that equation here. So that I think you have in your equation sheet. You see it's here. The magnetic force applied to a moving charge is Q times V times B. If the velocity and the magnetic field are parallel to each other, there is no force. If they are anti-parallel, there is no force. Any question? Okay, we're going to do some math, but I just want to give you. Let's take the right hand again. So let's review. This one you already know. So a current flowing is a moving charge. So the charge is moving in this direction. Yes? Right? Magnetic field is going that way, and you're going left. So the force is down. So the charge inside the wire will be deflected down. It will not accelerate, it will just be deflected. Now let's take this example here. It works the same way. You take your right hand. So that will be the velocity of the charge, that will be the magnetic field, that will be the force. So let's do the positive charge. The velocity is going this way, boom, 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 boom. Magnetic field is going towards you, boom. So the force is down. You see? And my hands, arms hurt. Okay? So again, if you have an issue with your right hand, just let me know. You can do it this way. Velocity this way, magnetic field towards you, force down. Okay? So you do it this way. The force is going this way. Okay? And the magnetic field is towards you. So the force will be down. So what's happening? How do you know which way it's going to turn? It says, I want to go in a straight line at a constant speed. No, you can't. Okay? You have to be deflected. You cannot be accelerated. You will be deflected. That's the law. Now, if the charge is negative, it will be the opposite. Okay? You can take your left hand, right? So left hand, velocity this way, magnetic field is towards you, the force will be up. Okay, so now the force is up. Don't space out. If you space out, told you ChatGPT will not help. This way. I want to go in a straight line. No, you have to turn this way. That will be the magnetic force, right? Is that clear? So if you have a moving charge inside the magnetic field, it will be deflected. Now, if you have the magnetic field everywhere, then the charge will go into a circle. This way, if it's a positive charge, this way it will be a negative charge. Okay, it will go around a circle. Okay, so again, take your right hand, don't be shy, wave at me, hello. Right? The charge going up, magnetic field into the board, the force will go this way. If you don't do it, you will not do it at all. You will be stuck for 5 hours and 10 hours. And I hope you will share the answer, right? So this way, magnetic field turn into the board, so the force will go in this way, it will be deflected that way. The negative charge will be deflected this way. Okay? Now, if you want to do it this way, the velocity will go this way, this finger, magnetic field goes that way, the force goes this way. So I want to go straight line at a constant speed. No, you can't. You have to make a turn. Okay. As a particle in a magnetic field is found to have zero magnetic force on it. If the particle is neutral, can you have a magnetic force? Neutral, a neutron. No, very good, because Q equals 0, no force. If the particle is stationary, so no velocity, can you have a force? No, very good. If the particle is along the magnetic field, can you have a force? No. If opposite to the magnetic field, can you have a force? No. All of them are possible. Okay? So for a magnetic field to act on a particle, it has to be charged, it has to be moving, and it has to be moving at a direction with the magnetic field. Okay, I repeat over and 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 over again. Okay, do this, including the direction. Do it, do it, do it, do it. I tell you, if you don't do it now, you won't do it for the test number 3 and you will suffer and you will hate me, which is fine, I don't care.
I just need the first half.
No, that's the makeup is just the second half.
Oh,
Yeah, just put your name. Oh, yeah. Oh, la, la. So 3 protons. So this way, let's find the force first, right? And then we find the magnitude. Take your right hand. Okay. The first one, the velocity is going this way. Magnetic field is going up. So the force is out on the screen towards you. Okay? Mm-hmm. If it's a positive charge, if it's negative charge, it's the opposite. Now this one is going to be just the opposite. The force will be into the screen. Do we have a force for number 2? No force. Okay. Okay, so what's the force? F in magnitude equals Q V B, and then the angle between V and B. So in that case, we said it's towards you, right? This towards you. Towards you is this. Here the force equals to 0, and here the force is into the screen. Thank you. Okay, so the force will be proton. So a proton yes, thank you. 1.6 times 10 to the negative 19. And then the velocity is, so it's mega, 2 times 10 to the 6. Okay. B is 0, 1. And that will be sine 90. Negative 14. Thank you. Newton. Toward. U. Or sometimes it says out of the screen. Okay? And here there is no force. Okay, 3.2 times 10 to the negative 14. Okay, so we are not going to do all of them, some of them, just to make sure you remember the units. Let's do number 1. Okay, so you have the charge. Q is 30. So 30 times 10 to the negative 9 coulombs. So that will be the speed. And that will be the magnetic field. So 50 times 10 to the negative 3 Tesla. And that means that the angle is 90 degrees. Okay, so this is the angle between V and B. Okay, so the force is QVB sine of the angle, right? So it's going to be Q, which is 30 times 10 to the negative 9, V, which is 12, B, 50 times 10 to negative 3, and that will be times 1. Okay. So that will be 2 times 10 to the negative 9 Newton. Is that clear? We good? It's not hard, right? It's just QVB. Uh, so for an electron, everything is the opposite, right? So let's do number 3, for example. Electron, you can use your left hand, or you use your right hand and you take the opposite. Okay, we have to hurry up. So what is the direction of the force of a vertical magnetic field upward? So now the magnetic field is going this way. East. So I don't know where is east, but I'm gonna say east is this way. So you have an electron going east. Okay, question. Where is the force? Is it toward you or away from you? Out of the board or into the board? So you can use your left hand because it's an electron, or you use your right hand and you do the opposite. So if I use my left hand, the velocity is going this way, magnetic field is going up. So where is the force? Into the ball. Or you can use your right hand and say, it's out of the ball and then it's you. Maybe it's not a right? So velocity, into the board, away from you, into the screen. So to say that it's going to be into the screen, we make a cross. That means into the screen because it's like an arrow, right? So this is the pointy thing, and this is the tail. The tail has like feathers, so you see the tail. Okay. So I can look at my sidekick here. You see? Remember how to do it. It's not that obvious because sometimes you are confused which way it's going to turn. So right hand this way, move that way. Magnetic field is inside the ball, as you see the cross. The force is there. So the particle wants to keep going straight line at a constant speed. No, you can't. You have to be reflected. Reflected will be counterclockwise. If it's negative, it's going to be counterclockwise. So we're going to use that for a mass spectrometer. So when you have a bunch of isotopes, they have the same charge. And they're going to go inside the magnetic field with the same velocity. Okay, so let's say you have isotopes of neon. Neon has isotopes 20, 21, 22. They have the same charge. So we strip them from an electron. But they have different masses. So we want to sort them out according to their masses. How many isotope 20 do you have? How many isotope 21 do you have? How many isotope 22 do you have? So you have them with the same velocity go inside the magnetic field. So they will be deflected, but the one with the largest mass will be deflected the least because it has more inertia. Okay, so if you apply the same force to a truck or to a bicycle will make a sharp turn, and the truck, has more inertia. Okay, it's called mass spectrometer. We can sort out isotopes and we can find the mass of isotopes. Okay, so let's try to find the equation. Let's try to find the equation for the mass spectrometer. I'm going to show you an app. If I find the app. So you use mass spectrometers all the time in the medical field, in biology, in chemistry. Ah, bless you. If it was magnetic field, no. No, yes. Okay, so let's take a guess here. So it depends on the magnetic field, depends on the velocity, it depends on the mass. And let's take a positive charge. Okay. Which way is going to be deflected? To the right or to the left? To the right, you think? it's a positive charge. Take your right hand. Moving this way. You agree? Where is the magnetic field? Magnetic field, you see the crosses into the board. So where is the force? Left. So it's saying be deflated to the left. So it's going to be deflated to the left. Because it's positive. If it's negative, it will be to the right. So the velocity is going this way, so up. Yes, so the direction of the charge is up, the velocity is upward. So it's coming this way, it's coming up. Magnetic field is into the board, velocity is to the left. Okay? So what do you think it depends on? If now I make it, if I make it faster, so it's going to make a turn, but the turn will be sharp or larger. Yes, very good. It will be a larger turn. Okay, so the turn, which is the radius, depends on the velocity, how fast, right? What do you think if I increase the magnetic field? So I increase the motivation. What do you think is going to happen? Sharp or yeah, sharper, right? Increase the motivation. You are increasing the motivation. It's got more motivated, sharper turn. Larger velocity, larger turn, okay, because it has more momentum. So it's kind of, I don't want to do it. I'm busy. I'm going really fast. No. You have to turn. So less motivation. Magnetic field, more motivation. And yes, and the charge, more motivation as well. So smaller radius. Do you agree? What about the mass? If you increase the mass, longer turn, very good, because more inertia, right? So conclusion, just without, we can do the math, but just out of the guts. Okay, the guts knows physics. So the radius, so this is the radius, right? That little turn here is the radius, depends on the mass. So if you have larger mass, you know, the turn will be larger, right? Because it has more inertia. Okay, it's harder to make it turn. It depends, it's proportional to the velocity, because larger velocity, more momentum. Once you have momentum, you know, you go very fast on the highway, it will make it very hard to make your turn. But it's inversely proportional to the charge. So more charge, more motivation to turn. Inversely proportional to the magnetic field. More magnetic field, more motivation. Okay? So if you have isotopes or any charged molecule and you don't know the mass, okay, so you can get the velocity, okay, that the velocity will be known, the magnetic field and Q. You can find the mass if you find the radius. Once you have the radius, you have the mass. So that's how a mass spectrometer works. Is to find the mass of isotopes or just to sort out isotopes. Agree? Okay, so you see, this unit is mostly conceptual questions. I make it very easy, but you just have to pay attention. So you have a bunch of isotopes, so a bunch of particles or isotopes, right? So you remove the electrons, they become charged. You make sure they enter the magnetic field with the same velocity. And the turn here, the radius depends only on the mass. And you have this equation here. You see, the radius will be proportional to the mass, proportional to the actually is the momentum, proportional to the momentum, inversely proportional to Q, inversely proportional to B. Okay, so just to give you an idea, so we can go back to that next time. So then that's my big idea. So let's go back to here. And okay, it's gonna be very important. That's how we'll see that next time.